Hello guys, you're welcome back to the reaction zone. In today's lesson, we're going to look at properties exhibiting periodicity. To start with, we're going to look at the concept of periodicity. Periodicity is the repetition or the reoccurrence of similar physical and chemical properties at regular intervals when elements are arranged in order of increasing atomic number in the periodic table. Periodicity is as a result of similar electronic configuration, especially valence shell electronic configuration in the periodic table. This is usually found among elements that belong to a particular group. Elements of a particular group have the same valence shell electronic configuration, and this is responsible for these elements having similar chemical properties. There are several properties that exhibit periodicity, and we're going to look at two of them in this class. The first one is atomic size, and the second one is ionization energy. An atom is assumed to be spherical, and atomic size is usually given in terms of the radius of a sphere. Atomic size can be defined as the distance from the nucleus to the outermost electron shell. It is actually difficult to determine the exact size of an atom for so many reasons. The first one is due to the small size of an atom. The size of an atom is about 1.2 times 10 raised to the power minus 10 meters. The second one is due to the fact that it is difficult to get an isolated atom. This is because the electron density around an atom usually coincides with that of neighboring atoms. And then, the third one is that an atom does not have a well-defined boundary. This is because the probability of finding an electron is never zero, irrespective of the distance of the electron from the nucleus. So, as a result of this, atomic size or atomic radius is usually defined in terms of the covalent radius. And the covalent radius is simply half the distance between the nuclei of two neighboring atoms that are bonded together by a single covalent bond. So this and this represent the nuclei of these two atoms. We can call these two atoms A and B. The distance between them is represented by this. Half the distance of these two nuclei is represented by this. So, atomic size is usually defined in terms of the covalent radius, which is half the distance between the nuclei of two neighboring atoms bonded together by a single covalent bond. Now, the next thing we're going to look at is how atomic size or atomic radius varies across a period and varies down the group. Atomic size decreases as you move from left to right across a period. The reason is because When you look at the elements of a particular period, for instance, looking at the elements of period 2, which starts from lithium down to neon, you can see that each of the elements in this second period has 2 electron shells each. So, in a particular period, the electron shells are constant. The number of electron shells are constant. However, the nuclear charge increases from left to right across the period. Also, the effective nuclear charge also increases from left to right across the period. Now, what that means is that as you move from left to right across the period, the force of attraction of the nucleus for the electrons increases. And what this brings about is a shrinking or a contraction in size of atoms as you move from left to right across the period. So because of the increase in nuclear charge across the period, as well as the increase in effective nuclear charge across the period as you move from left to right, atomic size decreases. Down the group, atomic size increases. Now, as you move down a group, for instance, this is group 1. You can see that the first member has 1 electron shell. The second member has 2 electron shells. The third member that is not shown here will have 3 electron shells, and so on and so forth. Now, as you move down a group, nuclear charge increases, but the effect of the nuclear charge is outweighed by the increasing number of electron shells as you move down a group. So, the increasing number of electron shells as you move down a group outweighs the effect of the nuclear charge. And that is why as you move down a group, atomic size increases. The second one we're going to look at is ionization energy. Ionization energy is the energy that is required to remove an electron from an atom in the gaseous state. Ionization energy generally increases from left to right across the period for several reasons. One is because of the nuclear charge. As you move from left to right across the period, nuclear charge increases. And what that means is that the force of attraction of the nucleus for the electrons increases as you move from left to right. So what that means is that as you are moving from left to right across the period, the energy that is going to be required to remove an electron from an atom is going to increase, because as you are moving from left to right across a period, the electrons are more strongly attracted towards the nucleus. So because of that, ionization energy increases from left to right across a period. However, it is important to point out that there are exceptions to the trend of ionization energy across the period. The first exception is between beryllium and boron. The second exception is between nitrogen and oxygen. Now, for us to understand these exceptions, it is important for us to arrange the electrons in orbitals. Now, beryllium has an atomic number of 4. So the electrons will be in the 1s and the 2s orbitals. Boron, on the other hand, has an atomic number of 5. So the electrons will be in the 1s, the 2s, as well as the 2p orbital. Ordinarily, going by the trend of ionization energy across a period, boron is supposed to have a greater ionization energy than beryllium. But in reality, beryllium has a greater ionization energy than boron. Why? Because of a field subshell. The 2s subshell is filled with 2 electrons, and the energy required to remove one of these electrons from this pair is greater than the energy required to remove this unpaired electron in the 2px orbital. So that's the reason why beryllium has a greater ionization energy than boron, because it has a filled subshell. That is, the 2s subshell is completely filled with electrons, and the energy required to remove an electron from this pair is greater than the energy required to remove this unpaired electron. The second exception is between nitrogen and oxygen. Now, nitrogen has an atomic number of 7. And the electrons are arranged as follows: 2px, 2py, and 2pz. 2 electrons here, 2 electrons here, 1, 1, 1. Oxygen, on the other hand, has an atomic number of 8. And the electrons are as follows: the 1s, the 2s, as well as the 2px, the 2py, and the 2pz. So there are 2 electrons here, 2 electrons here, 1, 1, 1, and an additional one here. When you look at the arrangement of the electrons in the nitrogen atom, which is this, you can see that the p subshell is half filled. The p subshell can take a maximum of 6 electrons, and it contains exactly 3. So the half-filled p orbital in nitrogen confers on it stability. Why? Because it minimizes electron-electron repulsion due to the fact that it is half-filled. However, when you look at the p orbital in oxygen, it is not half-filled. The electrons in the 2px are paired. Now, this will bring about electron-electron repulsion, which will make it much more easier to remove an electron from the p orbital here than to remove an electron from the p orbital in nitrogen. As a result of that, nitrogen has a greater ionization energy than oxygen. This is another exception to the trend across the period. Also, ionization energy decreases down the group. This is as a result of screening effect. The screening effect of outer electrons by inner electrons further increases the distance of outer electrons from the nucleus. As a result, outer electrons are under a reduced influence or effect of the nuclear charge. And what this means is that as a result of the screening effect, that the force of attraction of the nucleus for the outer electrons or the outermost electrons is reduced. And as a result of this, the energy that is required to remove outermost electrons as you move down the group reduces. So what this means is that ionization energy decreases as you move down the group. Thank you very much for watching this video. and see you in the next one.